A spiral galaxy is a certain kind of galaxy originally described by Edwin Hubble in his 1936 work The Realm of the Nebulae, and, as such, forms part of the Hubble sequence. Spiral galaxies consist of a flat, rotating disk containing stars, gas and dust, and a central concentration of stars known as the bulge. These are surrounded by a much fainter halo of stars, many of which reside in globular clusters. Spiral galaxies are named for the spiral structures that extend from the center into the galactic disk. The spiral arms are sites of ongoing star formation and are brighter than the surrounding disk because of the young, hot-up stars that inhabit them. Roughly two-thirds of all spirals are observed to have an additional component in the form of a bar-like structure extending from the central bulge, at the ends of which the spiral arms begin. The proportion of barred spirals relative to the barless cousins has changed over the history of the universe, with only about 10% containing bars about 8 billion years ago, to roughly a quarter 2.5 billion years ago, until present, where over two-thirds of the galaxies in the visible universe have bars. Our own Milky Way has recently been confirmed to be a barred spiral, although the bar itself is difficult to observe from the Earth's current position within the galactic disk. The most convincing evidence for its existence comes from a recent survey performed by the Spitzer Space Telescope of stars in the galactic center. Together with irregular galaxies, spiral galaxies make up approximately 60% of galaxies in the local universe. They are mostly found in low-density regions and are rare in the centers of galaxy clusters. Structure: spiral galaxies consist of 5 distinct components: a flat, rotating disk of stars and interstellar matter, a central stellar bulge of mainly older stars, which resembles an elliptical galaxy, a near-spherical halo of stars, including many in globular clusters, a supermassive black hole at the very center of the central bulge, a near-spherical dark matter halo. The relative importance, in terms of mass, brightness and size, of the different components varies from galaxy to galaxy. Spiral arms are regions of stars that extend from the center of spiral and barred spiral galaxies. These long, thin regions resemble a spiral and thus give spiral galaxies the name. Naturally, different classifications of spiral galaxies have distinct arm structures. SC and SBC galaxies, for instance, have very loose arms, whereas SR and SBA galaxies have tightly wrapped arms. Either way, spiral arms contain many young, blue stars, which make the arms so bright. Galactic bulge. A bulge is a huge, tightly packed group of stars. The term commonly refers to the central group of stars found in most spiral galaxies. Using the Hubble classification, the bulge of SR galaxies is usually composed of population II stars, that are old, red stars with low metal content. Further, the bulge of SR and SBA galaxies tends to be large. In contrast, the bulges of SC and SBC galaxies are much smaller and are composed of young, blue population I stars. Some bulges have similar properties to those of elliptical galaxies, others simply appear as higher density centers of disks, with properties similar to disk galaxies. Many bulges are thought to host a supermassive black hole at the centers. Such black holes have never been directly observed, but many indirect proofs exist. In our own galaxy, for instance, the object called Sagittarius A** is believed to be a supermassive black hole. There is a tight correlation between the mass of the black hole and the velocity dispersion of the stars in the bulge, the m-sigma relation. Galactic galactic spheroid. The bulk of the stars in a spiral galaxy are located either close to a single plane in more or less conventional circular orbits around the center of the galaxy, or in a spheroidal galactic bulge around the galactic core. However, some stars inhabit a spheroidal halo, a galactic spheroid, a type of galactic halo. The orbital behavior of these stars is disputed, but they may describe retrograde and/or highly inclined orbits, or not move in regular orbits at all. Halo stars may be acquired from small galaxies which fall into and merge with the spiral galaxy. For example, the Sagittarius dwarf spheroidal galaxy is in the process of merging with the Milky Way, and observations show that some stars in the halo of the Milky Way have been acquired from it. Unlike the galactic disk, the halo seems to be free of dust, and in further contrast, stars in the galactic halo are of population 2, much older and with much lower metallicity than the population I cousins in the galactic disk. The galactic halo also contains many globular clusters. The motion of halo stars does bring them through the disk on occasion, and a number of small red dwarfs close to the Sun are thought to belong to the galactic halo. For example, Captain's Star and Groombridge 1830. Due to their irregular movement around the center of the galaxy, if they do so at all, these stars often display unusually high proper motion. In 2013 and 2014 papers were published presenting evidence that the spheroid is actually a planar structure in about half of all galaxies. Oldest spiral galaxy. The oldest spiral galaxy on file is BX 442. At 11 billion years old, it is more than 2 billion years older than any previous discovery. Researchers think the galaxy's shape is caused by the gravitational influence of a companion dwarf galaxy. Computer models based on that assumption indicate that BX 442's spiral structure will last about 100 million years. Origin of the spiral structure. The pioneer of studies of the rotation of the galaxy and the formation of the spiral arms was Bertil Lindblad in 1925. He realized that the idea of stars arranged permanently in a spiral shape was untenable, since the angular speed of rotation of the galactic disk varies with distance from the center of the galaxy. A radial arm would quickly become curved as the galaxy rotates. The arm would, after a few galactic rotations, become increasingly curved and wind around the galaxy ever tighter. This is called the winding problem. Measurements in the late 1960s showed that the orbital velocity of stars in spiral galaxies with respect to the distance from the galactic center is indeed higher than expected from Newtonian dynamics, but still cannot explain the stability of the spiral structure. Since the 1960s, there have been two leading hypotheses or models for the spiral structures of galaxies: star formation caused by density waves in the galactic disk of the galaxy. The SSPSF model, star formation caused by shock waves in the interstellar medium. These different hypotheses do not have to be mutually exclusive, as they may explain different types of spiral arms. Density wave model. Bertil Lindblad proposed that the arms represent regions of enhanced density that rotate more slowly than the galaxy's stars and gas. As gas enters a density wave, it gets squeezed and makes new stars, some of which are short-lived blue stars that light the arms. This idea was developed into density wave theory by C.C. Lin and Frank Hsu in 1964. Historical theory of Lin and Xu. The first acceptable theory for the spiral structure was devised by C. Lin and Frank Xu in 1964, attempting to explain the large-scale structure of spirals in terms of a small amplitude wave propagating with fixed angular velocity, that revolves around the galaxy at a speed different from that of the galaxy's gas and stars. They suggested that the spiral arms were manifestations of spiral density waves. They assumed that the stars travel in slightly elliptical orbits, and that the orientations of their orbits is correlated i.e., the ellipses vary in their orientation in a smooth way with increasing distance from the galactic center. This is illustrated in the diagram. It is clear that the elliptical orbits come close together in certain areas to give the effect of arms. Stars therefore do not remain forever in the position that we now see them in, but pass through the arms as they travel in their orbits. Star formation caused by density waves. The following hypotheses exist for star formation caused by density waves. As gas clouds move into the density wave, the local mass density increases. Since the criteria for cloud collapse depends on density, a higher density makes it more likely for clouds to collapse and form stars. As the compression wave goes through, it triggers star formation on the leading edge of the spiral arms. As clouds get swept up by the spiral arms, they collide with one another and drive shock waves through the gas, which in turn causes the gas to collapse and form stars. More young stars in spiral arms. The arms appear brighter because there are more young stars. These massive, bright stars also die out quickly, which would leave just the darker background stellar distribution behind the waves, hence making the waves visible. While stars, therefore, do not remain forever in the position that we now see them in, they also do not follow the arms. The arms simply appear to pass through the stars as the stars travel in their orbits. Alignment of spin axis with cosmic voids. Recent results suggest that the orientation of the spin axis of spiral galaxies is not a chance result, but instead they are preferentially aligned along the surface of cosmic voids. That is, spiral galaxies tend to be oriented at a high angle of inclination relative to the large-scale structure of the surroundings. They have been described as lining up like beads on a string, with their axis of rotation following the filaments around the edges of the voids. Gravitationally aligned orbits. Charles Francis and Eric Anderson showed from observations of motions of over 20,000 local stars that stars to move along spiral arms, and described how mutual gravity between stars causes orbits to align on logarithmic spirals. When the theory is applied to gas, collisions between gas clouds generate the molecular clouds in which new stars form, and evolution towards grand design bisymmetric spirals is explained. Spiral nebula. Spiral nebula was a term used to describe galaxies with a visible spiral structure, such as the Whirlpool galaxy, before it was understood that these objects existed outside our Milky Way galaxy. The question of whether such objects were separate galaxies independent of the Milky Way, or a type of nebula existing within our own galaxy, was the subject of the great debate of 1920 between Heber Curtis of Lick Observatory and Harlow Shapley of Mount Wilson Observatory. Beginning in 1923, Edwin Hubble observed Cepheid variables in several spiral nebulae, including the so-called Andromeda Nebula, proving that there are, in fact, entire galaxies outside our own. The term spiral nebula has since fallen into disuse. Milky Way. The Milky Way was once considered an ordinary spiral galaxy. Astronomers first began to suspect that the Milky Way is a barred spiral galaxy in the 1990s. The suspicions were confirmed by Spitzer Space Telescope observations in 2005. which showed that the Milky Way's central bar is larger than was previously suspected. Famous examples